Yo, that's so cool. Let me try that. Hey, why did I tip over?
The reason why that happened to you, Muhammad, is because of a concept called tipping in biomechanics. Let me explain. Here, the box is resting on the ground. Gravity pulls down the box with a force called the weight, known as Fw. At the same time, the ground pushes up with a normal force, Fn, which exactly balances the weight. Notice how the weight force lines up straight through the center of the box and falls inside the base. As long as the center of mass stays inside the base like this, the box is stable. It won't tip over, even if you push it a little. Now, here in the second image, I'm applying a force and starting to tip the box. You can see that the box is rotating about its corner. The normal force, Fn, has shifted all the way to just that one corner. The other parts of the base are actually lifted off the ground. They aren't in contact anymore. Also notice where the weight force, Fw, is now. It's not above the base, it's outside of it. This is really important. When the center of mass moves past the edge of the base, gravity starts creating a moment that wants to rotate the box even more. At this point, the box is no longer balanced, and tipping has started. The ground can't push back with a normal force over the whole bottom anymore. It's only pushing up at the pivot point. Once this happens, unless another force stops it, the box will keep rotating and eventually fall over completely. So to summarize, tipping happens when the center of mass moves past the base. The normal force shifts to a single point and gravity causes the object to rotate, and that's why you tipped.
We've all seen it. Michael Jackson leaning forward at an impossible 50-degree angle. Body straight, heels on the ground, and somehow he does not fall. But if we pause the performance and analyze the forces at play, does this lean actually hold up in real life? Or does it defy physics? Let's break it down. To analyze the situation, we will model Michael Jackson as a rigid body leaning forward at a 50-degree angle. His feet are flat and fixed on the ground. The information that we have is Michael's height, his mass, and his shoe size. Now we need to understand the forces acting on him. The most important of these is gravity. Gravity will act on his mass at his center of mass, which in this case we will assume to be halfway through his body, right here. Given that his height is 1.75 meters and his mass is 53.297 kilograms, through his center of mass, we calculate the force of gravity, or weight, as given right here. And we find that to be 522.844 newtons. This force is what's trying to pull him down. But the key question is, how much torque or rotational force does this weight produce above the toes? To calculate that, we need the horizontal distance between the pivot point and the line of action of the weight. Let's take our pivot point as the tip of the toe, and the line of action of the weight in this case would be calculated right here. So since he's leaning at a 50-degree angle, you would calculate it as 1.75 over 2 times cosine 50. This would give us half the value right here. And then you would subtract 0.264, which is the size of Michael's shoe, to get 0.296 meters. This means that the line of action of the moment is 0.296 meters away from the pivot point. And that's what causes the torque. Let's use that to sum the moments around the tip of the toe. We use his weight, which is acting 0.296 meters, and we find that moment equals negative 154.76 Newton meters. Are there any other forces acting on Michael? There is. There's the normal force, but in this case the normal force is acting at the tip of the toe, which is the same as the pivot point. That means the normal force would be excluded from the moment equation. Therefore, the moment equation does not equal 0. It's unbalanced. There is a torque, and Michael should tip. But he does not. So, Now you might ask, how would Michael do this? Is Michael just him? Or is there more to it? Critics have been arguing about this for a long time, and the resounding conclusion that they came to is that Michael had a nail in his shoe. What does this mean? This means that the nail would be exerting a force on Michael that would prevent him from tipping. A force that would bring the sum of moment about the pivot point to 0. After thorough research, we have modeled the screw as 3 inches long, which translates to 0.0762 meters. And since the force would be distributed uniformly across the entire screw, we have determined that the resultant force on the screw would apply on Michael, that would apply on Michael would originate from the middle of the screw, about 0.0381 meters above the pivot point. Therefore, with this information, we can set a new sum of moment equation about Michael's toe tip. Now we have two forces acting in the opposite direction. And using this equation, we know that it should equal 0 since Michael is not moving. We can solve this equation for F nail to find the force of the nail, that would be the force that the nail would apply on Michael to prevent him from tipping over. And we find that to be 4,089.501 Newton.